Hello, this is Gary LaRude, Technical Editor at Microwave Journal. Welcome to today's EDICONonline workshop on mmWave LTCC components. Before we begin, let me introduce you to our platform. In the center of your screen, you'll see a window containing the presentation. To better see the slides, you can enlarge this to full screen. The window labeled Resource List contains a copy of the presentation and other resources. The workshop will be available to view on demand later, which will allow you to watch it again and recommend it to colleagues. You can even use the paper airplane icon at the bottom of your screen to invite colleagues right now so they can join the live presentation. If you have technical problems, please click on the yellow box with the question mark at the bottom of your screen for a user's guide. Today's presentation will be given by Aaron Vaisman of Mini-Circuits. For his full biography, please check the biography box in the lower left corner of your screen. After Aaron's presentation, we will have time for questions. If you have one, please type it in the Q&A box on your screen at any time. Aaron, I will turn the session over to you.
Gary, many thanks for your kind introduction. And welcome all to this presentation on LTCC. On my presentation on the journey to LTCC solutions for millimeter wave applications, we spent a good time talking about Mini-Circuits technological advancements in LTCC enabling component developments in the millimeter wave spectrum. The emphasis was primarily on the engineering of new material systems, mainly powders and conductive pastes, along with the development of a photoimaginable paste etching process which delivers a much improved fidelity on the layout traces. We also discussed how these new material systems enable the implementation of much needed transmission line based topologies, including distributed edge and broadside coupled structures and SIWs, substrate integrated waveguides. The new powders present a much refined, isomorphic, uniform, granular structure, effectively smoothing the surfaces over which the metal traces are being laid out. This results in very noticeable insertion loss reductions, especially on narrow bandpass filters, or narrow bandwidths, to be more specific. On the other hand, a photoimaginable screen printing process delivers much smoother conductor traces, fine-line definitions, allows for much tighter spacings between conductors, along with a much higher silver concentration of the paste. This translates into the possibility of realizing tighter couplings, reducing lot-to-lot, unit-to-unit variations, significantly reducing insertion losses by having much smoother and higher conductivity conductors. One thing we realize is that any work at millimeter waves is truly custom in the sense that it is almost impossible to employ off-the-shelf parts without having something to be modified. For instance, not everyone uses the same substrates nor thicknesses or multi-layer stock-ups to implement their motherboards. The diversity on these requires a close attention to the way a filter will be interfaced with its motherboard. It requires careful design of launches and interfaces to other surrounding components. Designs such as bandpass filters are varied from application to application on center, cutoff, and stop and rejection frequencies, as well as levels of insertion loss, return loss, and so on. When you cater more than 20,000 customers, as we do here at Mini-Circuits, believe me, there are many flavors to a bandpass filter request center at the same frequency. This greatly exacerbates at millimeter waves, since the percentage bandwidths translate into massive absolute bandwidths. So custom designs are the new norm at these frequencies. Custom design developments demand a change in the design flow to ensure a first spin pass success. That's the ultimate goal to us. The development of new material systems and the employment of the same for the implementation of brand new topologies requires deep knowledge of the material properties and the process-related limitations to ensure a first spin pass success. Basically, we at Mini-Circuits quickly realized that a thorough material characterization up to the high frequencies of the mmWave range was required so our full 3D simulation models will be refined. At the same time, we also recognized that any design at those high frequencies would pretty much constitute a custom design. As previously mentioned, this is given the complications added by working at these frequencies where the performance of the components is so much linked to the motherboard substrate stock-up, launch designs, surrounding elements, radiative losses, fringing fields, just to name a few of them. A custom job is typically expensive since it is by definition hand-tailored to a very specific application. For instance, several different customers may request a bandpass centered at 28.5 GHz, but each requiring a complete different percentage bandwidth. This would make the development of each one of these filters unique. A solution to the above listed problems was required, and the answer laid on characterizing the material properties for each one of these material systems, as well as internally designing software tools to assist in the design, automation processes, and the creation of simulation models. Ultimately, our objectives are to achieve a first spin success as a first measure here. Second, being capable of providing SMP files to our customers way ahead the time prototypes are made available, so this simulation-based data can be employed by system-level engineers in incorporating, laying out, and gauging the impact on the overall system due to the use of our parts, way in advance of the fabrication of the same. Third, develop custom designs on a highly collaborative manner, on a timely manner, and cost effectively. Being capable of monitoring, as a fourth item, being capable of monitoring the performance of the units, raw materials involved, and the overall process performance on a lot-to-lot basis. To these objectives, we created test coupons made of several different methods. We have here a picture of an actual test coupon employed in the material characterization of our LTCC material systems. Within this test coupon, we have several different structures. We have de-embedded capacitors, resonating structures, multi-mole resonators, delay line-based components. To measure the dispersive and anisotropic nature of the decay and loss tangent of several different material systems, as well as the conductivity of different pastes, this test coupon was actually fabricated. We use probing as a method to test the same, and a homebrew algorithm to capture the actual measurement data on the parameters of interest, mainly decay and loss tangent. This slide is something that we at Mini-Circuits would pride of. And it is so because it shows a comparison, a comparative plot between a simulation of a device versus the actual test measure data. We would like to emphasize here the striking similitude between the two traces. The gathered information on the master material properties yielded a substantial increase in our capability to predict electrical performance into the millimeter waves with a very high degree of confidence. This level of simulation model predictability is crucial to the custom design tasks required for millimeter wave applications. Once the material simulation models and the working circuit topologies had been defined, the next development stage was set to assist in the expedition of custom designs at mmWaves. This consisted in the incorporation of homebrew software tools geared to the automating the fine-tuning processes during the filtering structure implementations. The newly developed design process allows for much shorter design times on distributed topologies to be employed at very high frequencies. The actual design workflow goes through synthesis, diagnosis, tuning as a way to create custom-based designs. First and foremost, we get our customer specs, and those specs are entered through a synthesis process to quickly generate a circuital model of a filter and verify ideal performance of the same. This is what we call the circuital model. This circuital model then goes into a 3D layout / mapping process where we translate the actual circuital device into an actual geometrical 3D simulation model. That 3D simulation model generates on a FEM engine a simulation result, which may or may not be optimal. Most likely, it won't be optimal on the first pass, and most likely, maybe far away from being optimal. So what we do next is a diagnosis process. On this process, we extract equivalent circuit models from test data or simulation results. And this is proven to be a very useful step for the tuning process. Then we iterate on this cycle, on the circuital model generation, 3D layout mapping, simulation and diagnosis on a loop on an automated basis, calling up routines through Python scripting and MATLAB. The algorithms regarding tuning are linked with the simulation software and automatically modifies the parameters to achieve the desired performance. The optimized tuning process employs both known and lesser known space mapping techniques, along with artificial intelligence routines. This, I must admit, is a still ongoing and still under refinement process. Nevertheless, it already started to show great benefits. So with this, we get a full picture of MCL's mini circuits areas of investment in LTCC. I understand our time is limited today, but I really want to showcase some of the results obtained out of the integration of the technological advancements with the implementation of new topologies by employing carefully characterized material models within our simulators, performing automated design loops geared to the optimization of the component's performance, and finally, expanding our expertise with this technology as well as our long-standing experience in the manufacturing world and our broad selection of MMIC components to create hybrid package assemblies at cost-effective price points to cover for your needs and mmWaves. This has led us to the development of a new set of components. Well, most notoriously, we've developed filters and transformers. Also, it has given birth to a whole new category of component assemblies, namely a new product line of mmWave packages, which I would like to discuss separately. This is a very exciting area in development since the LTCC technology has naturally proven to be a great fit. I believe the kind of performance we're starting to see that are feasible by employing LTCC as a packaging technology are really encouraging, since this means that a cost-effective performing solution alternative is available in the LTCC technology to the current available chip and wire flip chip assembly schemes. MCL's new technological proposal will make out of those high-performance methods surface-mountable and cost-effective alternatives. I would like to bring up some examples of what has been simulated and is under construction, and it will be available within a couple of months from now, along with some more examples that have already been fabricated for which we have test data. So let me start with this distributed low-pass filter realization. With the new material systems and new topologies being employed, we have achieved lower in-band insertion losses. We are really trusting in these simulation models. This has been validated as shown on previous slides. So we expect that the actual end performance, measured performance, will be very close to what we're seeing today on these simulation plots. These simulation plots also show much deeper and broadband stop and rejections, sustained performances at frequencies beyond X-band, and we may actually provide surface-mountable shielding structures to alleviate some of the needs that are required for deep stop and rejections at very, very high frequencies, above 30 gigahertz or so. Another example of a realization of filters well into the millimeter waves is this couple of 5G-oriented bandpass filters. These are two filters that have already been designed and sent out for fabrication, targeting specifically bands 257, 258 of the upcoming 5G application standard. Again, we see much lower in-band insertion losses than traditional techniques, traditional materials previously employed by the LTCC industry. Mid-band insertion losses close to 1.3 dB, much deeper in broadband stop and rejections, below 30 dB at frequencies as high as 30, 40, even 45 gigahertz, although these simulation results are limited. But I may be available offline to provide you with much broader band simulation results on the same. Sustained performance at frequencies beyond X-band, and again, we will be providing, or we intend to provide, surface-mountable shielding structures as required. Here's another example of a distributed bandpass filter realization. This filter here has a center frequency at around 23, 24 gigahertz. This is an edge and broadside couple filtering structure. We present low emissions and high isolation on a broadband basis. And we're being aided here by a careful design of the launch to the filter, as well as a careful internal shielding of the filtering structure to accommodate for very, very high stop and rejections. We have also realized implementations of substrate integrated waveguide filters. What we're seeing today here at this slide are test measured results on two kinds of spins for the same actual topology. The blue plot shows the standard technological implementation on LTCC for this particular substrate integrated waveguide filter. We see very high insertion losses, mid-band insertion losses, with respect to a second spin on the same, employing the advanced technological materials which are composed of improved powders on the LTCC side, as well as conductive pastes on the conductor side. We're looking here at a substrate integrated waveguide centered at 28.5 gigahertz with a 7.3% bandwidth, with an impressive mid-band insertion loss below 1.5 dB. These substrate integrated waveguide topologies are enabling very narrow bandpass filter implementations with low losses up to the mmWave waves. We are developing as we speak, and we have actually implemented also on some of our developments, technological advances related to via implementations for these substantial waveguides. We're employing also higher conductivity silver pastes and lower loss dielectric materials. This slide here is an effort that we have initiated as an internal need for packaging our CAT series of mimic mmWave attenuators. Those CAT attenuators are readily available on die form currently in our website, but we wanted to provide our customers with a full turnkey package solution on the same. And we quickly realized that a QFN, plastic QFN approach to the same will act on the detrimental of the actual performance of these attenuators. So some key customers have commissioned custom designs for switches, attenuators, amplifiers, slow pads, and mixers following the success on this particular implementation. We currently have two technological offerings under qualification on this packaging technology. We're discussing today the LTCC approach, but I would like also to inform to you that we have a soft substrate version of the same. These packages are intended to operate in above 50 gigahertz, and we have test data that supports that viability. Speaking of test data, I want to share with you some of the test measure results on a CAT-2, which is a 2 dB attenuator as a package unit mounted on test board. You quickly notice that the insertion loss performance is pretty flat. It's around 2 dB all the way up to 55 gigahertz. And return losses are close to 15 dB or so, all the way up to the same frequency range. This is an impressive result, and we're very proud of it. You will see soon in our catalog a full lineup of components employing this packaging technology, starting with these CAT attenuators. Our packaging technology has not stopped at the common wire bonding approach. We are also experimenting with flip chip implementations. We have designed, in this actual slide, I'm showing here to you a picture of an LTCC interposer at which we have mounted a flip chip switch, single pole double throw switch, and I will soon show you test data on this development. As we speak, we are in the process of qualifying this actual technology. Speaking of test data, here we have test measure data on the single pole double throw flip chip assembled onto a LTCC interposer. This will be a great product offering in the sense that it will provide our customers with a surface mountable version of a well-performing switch all the way up to 55 gigahertz. As I mentioned before, we have not limited our packaging efforts to attenuators nor to switches, but we've moved forward with development of packages as well for samples, for instance. We're showing an open construction, basically, of our package with an LTCC substrate receiving an integrated circuit, a mimic circuit designed here at Mini-Circuits, a sampler to be more specific, which has been wire bonded with very low wire bonding profiles and employing a plastic lead as a cover to the full assembly. Performance on the same will be noticed on the next slide. So here we have the performance of our sampler. Very flat response on the coupling ratio around 25 dB, all the way up to 50 gigahertz. We should have measured actually this device to higher frequencies. It looks like there's good potential to have performance at higher frequencies as well. And with this, I would like to conclude my presentation for today. I appreciate the time that you've spent with me, and I hope this has been enjoyable. I highly encourage you to visit our website, www.minicircuits.com, for more information on our product offerings. And with this, I will lead you to our next section of question and answers.
Okay, we have a couple minutes for questions, so let's do those. Aaron, thank you very much for that interesting presentation.
Thank you all for staying with us.
The first question is, can LTCC filters be used for narrowband mmWave applications? And the viewer notes that the FCC defined 100 megahertz channels at 24 gigahertz in the recent auction, and the Korean and Japanese standards have 800 megahertz and 400 megahertz channels respectively at 28 gigahertz. So are the filters capable of handling those bandwidths?
Oh, that's a great question. So the short answer is yes. In theory, we could design in any filter with any percentage bandwidth within 3% all the way up to comfortably 35-40% bandwidths at those frequencies. The question that we will have to pose afterwards is how much insertion loss can we afford? And there's a theoretical relationship between the bandwidth of the filter to the insertion loss, being that as the percentage bandwidth gets narrower, the insertion loss, the mid-band insertion loss on the filter will increase for the same order of a filter, for the same topology of a filter. So the short answer is yes. And the counter question will be then how much insertion loss can we afford on a system level?
Got it. And let's squeeze in one more. One of our other viewers wanted to know some information about the EM simulation of the filter, which you touched on briefly. Can you talk any more about the tool you use?
Yeah, absolutely. So we combined a suite of software tools in order to realize these filters. And it's a combination between our homebrew algorithms as well as some other software-related design aids like method moments and FEM engines. In particular, we have employed for the filters that I have shown you, we employed an ADS solution for the method of moments, and we are employing an ANSYS solution for the full 3D simulation.
Very good. Unfortunately, we've run out of time for questions. We have another session starting. I'll remind everybody before we end that this presentation has been recorded and you will be able to watch it again on demand. You'll find it at the events section of the Microwave Journal and the Signal Integrity Journal website. So if you'd like to see it again or your colleagues would benefit from this workshop, please do let them know. Thanks again, Aaron and Mini Circuits, as well as all our sponsors who make EDICONonline possible. And I'll encourage you to stay with us for the next technical session, which is discussing 5G phased array antenna design, presented by Anil Pandey. Thanks, everyone.